Beneath a frozen shell thicker than Mount Everest is tall, an ocean larger than all of Earth's seas combined sits in complete darkness. You're probably picturing some distant exoplanet, maybe something thousands of light years away. Wrong. This ocean exists right here in our solar system, orbiting Jupiter every 3.5 days. Europa holds more liquid water than our entire planet, and NASA just launched a $5 billion mission to find out if anything is swimming in it. The numbers don't make sense at first. Europa is slightly smaller than our moon, yet somehow contains double the water volume of Earth. Where did it all come from? More importantly, how does it stay liquid when surface temperatures drop to -220 degrees Celsius? The answer involves one of the most violent gravitational relationships in the solar system, and it's the same force that might be creating the conditions for life to exist right now, roughly 390 million miles from the Sun. Jupiter's gravity doesn't just pull on Europa. It squeezes the Moon like a stress ball, over and over, every orbit. The result is tidal heating, a process so intense that it generates enough warmth to maintain a liquid ocean beneath an ice shell that would otherwise be frozen solid. But here's what makes this truly remarkable. The same gravitational torture that keeps the water liquid also cracks the ice above it, creating a dynamic surface that might be exchanging material between the frozen exterior and the hidden ocean below. Scientists discovered something strange when the Galileo spacecraft flew past Europa in the late 1990s. Jupiter's powerful magnetic field, which normally behaves in predictable ways, was getting disrupted near the Moon. Not scattered randomly, but in a pattern that suggested something conductive existed beneath the surface. The only substance that made sense was salt water, lots of it, creating its own induced magnetic field through interaction with Jupiter's magnetosphere. This wasn't speculation based on models. It was a direct measurement of something happening right then. The surface told its own story. Europa's ice shows almost no impact craters, which seems impossible for an object that's been orbiting Jupiter for billions of years. The solar system is full of debris, rocks, and ice chunks that should have been pounding this moon relentlessly. Yet Europa's surface is remarkably smooth, the smoothest solid object we've ever found. The only explanation that fits is resurfacing, ice that gets recycled and renewed, erasing old scars. Something beneath that crust is mobile enough to erase geological history. Look closer at Europa's surface and you'll see something that resembles pack ice on Earth's Arctic Ocean, except the pieces are the size of cities. These ice rafts have rotated, shifted, and refrozen in new positions. Some regions show what scientists call chaos terrain, areas where the surface has completely broken apart and reassembled into jumbled landscapes. The ice isn't just sitting there. It's moving, breaking, reforming. Underneath all that activity, an ocean is pushing upward. Then there are the streaks. Long linear features, reddish-brown in color, crisscross Europa's pale surface like veins. For years, scientists debated what these could be. Radiation damage? Mineral deposits? The answer turned out to be salt, specifically magnesium sulfate, left behind when briny water from below erupted onto the surface and evaporated. The ocean isn't just sitting quietly in the dark. It's interacting with the ice shell above it, possibly in ways that could bring nutrients down and waste products up, exactly the kind of exchange that life would need. Water alone doesn't make a habitable world. You need the right chemistry, the right energy sources, the right conditions maintained over geological timescales. Europa's ocean started out wrong for life, too acidic, loaded with sulfates and carbon dioxide. But something changed. Over 4.5 billion years, chemical reactions transformed that harsh environment into something that resembles Earth's oceans. The water became chloride-rich, with dissolved magnesium, sodium, potassium, and chlorine floating in concentrations similar to our seas. The ocean evolved. In 2024, the James Webb Space Telescope detected carbon dioxide on Europa's surface, specifically in a region called Terra Regio. This wasn't just any carbon dioxide. Analysis showed it came from below, from the subsurface ocean, deposited recently in geological terms. Carbon is fundamental to life as we know it. Finding it concentrated in an area where the ice has clearly been disrupted, where material from the ocean appears to have reached the surface, isn't proof of life. But it's exactly what you'd want to see if you were looking for habitable conditions. Then came the ammonia discovery. Scientists re-examining old Galileo data found faint signals of ammonia-bearing compounds near fractures in the ice. Ammonia matters for two reasons. First, it's a nitrogen-bearing molecule, and nitrogen is essential for amino acids, DNA, proteins, all the molecular machinery that biology runs on. Second, ammonia acts as antifreeze, lowering water's freezing point. In Europa's environment, where temperatures hover around freezing even in the ocean, ammonia could create pockets of liquid water that would otherwise freeze solid. Life, if it exists, might be clustering around these ammonia-rich zones. The energy question looms over everything. On Earth, most life ultimately depends on sunlight, either directly through photosynthesis or indirectly through food chains built on photosynthetic organisms. Europa receives 25 times less sunlight than Earth, and none of that reaches the ocean anyway. So where would the energy come from? Tidal heating provides warmth, but life needs chemical energy, electrons moving from one molecule to another, reactions that release usable power. One possibility involves the same process that supports life at hydrothermal vents on Earth's ocean floor. Hot water, heated by geological activity, erupts from cracks in the seafloor, carrying dissolved minerals and chemicals. When this hot, chemically rich water meets cold ocean water, reactions occur spontaneously. Microbes harvest the energy from these reactions, building entire ecosystems in complete darkness. Europa might have similar vents if its seafloor remains geologically active. That's where the debate gets contentious. Recent calculations from Washington University in St. Louis suggest Europa's seafloor might be cold and geologically quiet. The tidal heating that keeps the ocean liquid might not penetrate deep enough to warm the rocky core below. Without volcanic activity, without fracturing and faulting that exposes fresh rock to water, the chemical reactions that microbes could feed on become much harder to sustain. Europa's core likely cooled billions of years ago, and unlike Earth's interior, which still churns with heat from radioactive decay, Europa might not have enough internal energy to power active geology at the seafloor. But other researchers aren't convinced the story ends there. Even without volcanic hydrothermal vents, chemical energy could come from different sources. Radiation from Jupiter constantly bombards Europa's surface, breaking apart water molecules and creating hydrogen peroxide, oxygen, and other oxidants. These chemicals could work their way down through the ice, eventually reaching the ocean. Meanwhile, the seafloor, even if cold, still contains minerals that can react with water through a process called serpentinization. Mix oxidants from above with reduced minerals from below, and you've got potential energy for life. There's another pathway that nobody predicted until recently. The ice shell itself might be producing nutrients. Jupiter's radiation doesn't just create oxidants, it also generates complex organic molecules from simpler compounds on the surface. Normally, these would just accumulate in the ice, chemically isolated from the ocean. But a process called crustal delamination could change that. As denser, salt-rich ice forms near the surface, it could sink through the lighter ice below, carrying those surface nutrients down into the ocean like a conveyor belt. The ice shell wouldn't just be a barrier. It would be a chemical factory and delivery system. The plume question adds another layer of mystery. In 2012, the Hubble Space Telescope captured what appeared to be water vapor erupting from Europa's south polar region, shooting 200 kilometers into space, more than 20 times the height of Mount Everest. If real, these plumes would be a gift to future missions. Instead of drilling through miles of ice, a spacecraft could simply fly through a plume and collect samples of ocean water directly. But proving the plumes exist has been surprisingly difficult. Hubble saw the plume signature once, maybe twice. The Galileo spacecraft might have flown through one in 1997, though that interpretation came decades after the fact from reanalysis of magnetic field data. The James Webb Space Telescope looked for plumes in 2023 and found nothing. Other observations using radio telescopes searched for the molecules that should be present in plumes and came up empty. Either the plumes are rare, episodic events that only happen under specific conditions, or they're much weaker than initially thought, or some of those early detections were misinterpretations of noisy data. The uncertainty doesn't diminish Europa's potential. Plumes or no plumes, the ocean exists. The chemistry appears favorable. The energy sources, while debated, seem sufficient for at least microbial life. What Europa needs now is not more speculation from a distance, but direct investigation up close. That's exactly what NASA launched on October 14, 2024. Europa Clipper is the largest spacecraft NASA has ever built for a planetary mission. With its solar arrays deployed, it stretches over 100 feet, roughly the length of a basketball court. Those enormous solar panels are necessary because Jupiter sits 5 times farther from the Sun than Earth, meaning sunlight there is 25 times weaker. Clipper will spend 6 years traveling 1.8 billion miles, using gravity assists from Mars and Earth to slingshot itself toward Jupiter, arriving in April 2030. The mission design is clever out of necessity. Jupiter's radiation environment is brutal, intense enough to fry electronics in a matter of hours if a spacecraft stayed near Europa continuously. Instead, Clipper will orbit Jupiter itself, swooping past Europa for close flybys, then retreating to safer distances. Over 4 years, it will complete 49 of these flybys, each one bringing it within 16 miles of the surface in some cases. During each pass, the 9 instruments on board will have just minutes to gather data before radiation levels become dangerous again. Those instruments represent the cutting edge of planetary science. Radar will peer through the ice, measuring its thickness and looking for water pockets within the shell. Magnetometers will map Europa's induced magnetic field in far greater detail than Galileo could, potentially revealing the ocean's depth and salinity. Spectrometers will analyze the surface composition, identifying organic molecules, salts, and other chemicals that might have come from below. Cameras will image the surface at resolutions high enough to see features the size of a car. One instrument stands out for its potential to make history. The Surface Dust Analyzer will collect ice grains and dust particles as Clipper flies through the space just above Europa's surface. By analyzing the composition and trajectories of these particles, scientists can determine where they came from and what they're made of. If plumes exist, SUDA will fly right through them, collecting samples of ocean water without the spacecraft ever touching the surface. Laboratory tests have shown something remarkable about instruments like SUDA. Scientists fired ice grains containing tiny amounts of bacterial cell material at a prototype mass spectrometer under conditions simulating a Europa flyby. Even when only 1% of a grain consisted of biological material, the instrument detected it. Clipper carries similar technology. If microbial life exists in Europa's ocean, and if that life gets ejected into space through plumes or surface fractures, and if SUDA happens to sample those particles, the instrument could detect alien biology directly. Nobody on the mission is publicly betting on that outcome. The odds of all those conditions aligning seem astronomical. But the fact that it's even possible that we've built a spacecraft capable of detecting extraterrestrial life if it's there, represents a profound shift in space exploration. For perspective, we've never attempted anything quite like this before. Every previous mission to detect extraterrestrial life required landing, drilling, or direct sampling. Clipper could find it simply by flying through the right patch of space at the right moment. The margin for error is razor-thin, but the payoff would rewrite biology textbooks. Understanding what makes this possible requires examining Europa's surface in detail. When Voyager 1 flew past in 1979, it sent back images that baffled scientists. Europa looked nothing like a typical moon. No impact craters pockmarked the surface. No mountains broke the horizon. Instead, the images showed a smooth, cracked sphere crisscrossed by dark reddish-brown streaks and linear fractures stretching hundreds of miles. Those features told a story. The lack of craters meant the surface was young, geologically speaking, probably only 40 to 90 million years old. On cosmic timescales, that's yesterday. Something was constantly resurfacing Europa, erasing ancient impact scars. The cracks suggested movement, tectonic activity driven not by internal heat alone but by the flexing of the ice shell as Jupiter's gravity squeezed and released the moon every 5 days. The reddish-brown material coating those fractures became a mystery that took decades to solve. Early theories proposed sulfur compounds ejected from volcanic Io and deposited on Europa's surface. But spectroscopic analysis told a different story. The material appeared to be salts, magnesium sulfate primarily, mixed with other minerals. These weren't deposits from space. They came from below. When Europa's ice shell cracks under tidal stress, liquid water from the ocean can seep upward through the fractures. As it reaches the surface, the extreme cold and vacuum of space cause it to evaporate instantly, leaving behind dissolved salts and minerals. Those deposits form the reddish streaks we see. The color comes from radiation damage. Jupiter's intense magnetic field accelerates charged particles to enormous speeds, and when those particles slam into the surface, they break chemical bonds and create new compounds that absorb light differently. This process matters because it means Europa's surface isn't isolated from the ocean below. There's exchange happening, material moving between the deep ocean and the exposed surface. James Webb Space Telescope observations confirmed this in 2023 when astronomers detected carbon dioxide concentrated in a region called Terra Regio, an area of chaos terrain where the surface appears jumbled and disrupted. The carbon dioxide didn't come from space. Isotopic analysis showed it originated in the subsurface ocean and reached the surface recently, geologically speaking, probably within the last few hundred years. Terra Regio itself reveals how dynamic Europa's surface can be. Chaos terrain forms when warm ice or liquid water rises from below, melting or disrupting the overlying ice shell. The result looks chaotic because it is: blocks of ice tilted at odd angles, fractured and refrozen in new configurations, surface material replaced by fresher ice from deeper layers. These regions offer windows into Europa's interior composition. Then there's the question of plumes. In 2012, Hubble observations suggested water vapor erupting from Europa's south polar region, shooting 125 miles into space before falling back to the surface. The detection was tentative, based on ultraviolet spectroscopy showing what appeared to be hydrogen and oxygen atoms where none should be. Follow-up observations in 2016 provided additional evidence. Researchers analyzing old Galileo data discovered that when the spacecraft flew past Europa in 1997, it might have passed directly through a plume without anyone realizing it at the time. But plumes remain controversial. Later observations with more sensitive instruments found nothing. The James Webb Space Telescope examined Europa thoroughly and detected no active plumes. Radio telescope arrays saw no molecular emissions. Either the earlier detections were misinterpreted, or plumes on Europa are sporadic, erupting only occasionally under specific conditions. Models suggest that if plumes exist, they're most likely when Europa reaches the farthest point in its orbit from Jupiter. At that moment, tidal forces stretch the Moon maximally, potentially opening cracks wide enough for pressurized water to escape. The plumes wouldn't be steady geysers like those on Saturn's moon Enceladus. They'd be brief, localized eruptions that might occur every few orbits or less frequently still. This uncertainty actually increases Clipper's importance. The spacecraft will fly past Europa 49 times over 4 years, sampling different locations under different orbital conditions. If plumes exist, Clipper has excellent odds of encountering one. If they don't exist, or if they're too weak to detect remotely, Clipper will still gather material from Europa's exosphere, the thin envelope of gas and dust particles surrounding the Moon. Every object in space loses material to its surroundings. Solar radiation and Jupiter's magnetospheric particles constantly bombard Europa's surface, breaking molecular bonds and ejecting atoms and molecules into space. Some of that material escapes entirely. Some falls back. And some lingers in a thin cloud around the Moon. SUDA will sample that cloud, collecting particles that originated on the surface or potentially from the ocean itself if exchange processes are active. Recent discoveries add weight to the idea that Europa's surface and ocean communicate regularly. Analysis of old Galileo spectrometer data revealed ammonia-bearing compounds near surface fractures. Ammonia is significant for 2 reasons. First, it's a nitrogen compound, and nitrogen is essential for life as we know it, playing key roles in amino acids, DNA, and proteins. Second, ammonia lowers water's freezing point. An ocean containing dissolved ammonia could remain liquid at temperatures several degrees below 0 Celsius, potentially staying fluid even in regions where pure water would freeze. The ammonia detection came from reanalyzing data that had sat in archives for decades. Scientists applied modern processing techniques to old near-infrared observations and found faint spectral signatures that earlier analysis had missed. The compounds appeared concentrated near fractures and pits, exactly where you'd expect material from below to reach the surface. This pattern keeps repeating. Every time researchers look more carefully at Europa, they find more evidence of an active world. The surface isn't a static ice shell sitting atop a stagnant ocean. It's a dynamic interface where processes from below continuously reshape what we see from above. Cracks form and heal. Chaos terrain disrupts and refrees us. Salts and minerals migrate upward. Carbon dioxide deposits in specific locations. Ammonia appears near fractures. All of this paints Europa as a world where the ocean isn't sealed away forever beneath impenetrable ice. It's accessible, at least in principle. Material from the ocean reaches the surface through various processes. That's what makes Clipper's mission feasible without landing or drilling. The Moon itself brings samples to the surface. But here's what nobody can answer yet: how much exchange actually occurs? Is it constant and widespread, or rare and localized? Do these processes deliver enough material from the deep ocean to the surface that Clipper can sample it? Or does radiation and weathering destroy organic molecules before they can be detected? These questions matter because they determine what Clipper will find. If exchange is robust and frequent, the spacecraft should detect clear chemical signatures from the ocean, potentially including organic compounds or even biosignatures. If exchange is minimal or if surface conditions destroy delicate molecules quickly, Clipper might see only heavily altered material that doesn't reflect the ocean's true composition. The mission design acknowledges this uncertainty. Clipper's instruments are built to detect a wide range of compounds at very low concentrations. The radar can peer through several miles of ice, potentially detecting liquid water pockets trapped within the shell. Magnetometers will map the induced magnetic field with unprecedented precision, revealing ocean depth and conductivity. Cameras will image the surface at resolutions allowing scientists to identify the freshest terrain, where material from below reached the surface most recently. That last capability could prove crucial. If Clipper can identify very young surface features, areas that formed within the last few years or decades, those locations offer the best chance of finding pristine ocean material before radiation has had time to alter it significantly. Timing matters in ways that aren't immediately obvious. Europa's orbit creates predictable patterns. Every 3-5 days, the Moon completes one trip around Jupiter. That orbital period determines when tides peak, when ice flexes most dramatically, and potentially when material from below has the best chance of reaching the surface. Clipper's mission design accounts for this. The spacecraft won't arrive at random moments. Its flybys will be timed to capture Europa at different points in its orbital cycle, sampling conditions when tidal forces are strongest and when they're weakest. This approach should reveal whether surface activity varies with orbital position. But there's a complication. Europa's surface doesn't respond instantly to tidal forces. Ice has memory. When stress builds, cracks don't necessarily open immediately. They might propagate hours or days later. When tidal forces relax, fractures don't seal up right away. Material could continue rising through a crack long after the peak stress has passed. This delayed response makes prediction difficult. Scientists can calculate exactly when tidal forces reach maximum strength. They can't say with certainty when a particular crack will open or when water might breach the surface. Clipper will have to sample the Moon repeatedly, building statistical understanding of how surface activity correlates with orbital mechanics. The spacecraft's trajectory creates its own set of constraints. Radiation near Jupiter is intense. Europa orbits deep within Jupiter's magnetosphere, where trapped charged particles create a radiation environment that would destroy unshielded electronics within hours. Clipper can't orbit Europa directly because sustained exposure would kill the spacecraft. Instead, it orbits Jupiter on a highly elliptical path designed to bring it close to Europa periodically while spending most of its time farther out where radiation is less severe. Each close approach lasts only hours. The spacecraft swoops in, gathers data frantically, then retreats to a safer distance. Those brief encounters must be choreographed precisely. Different instruments need different viewing geometries. Cameras want sunlight illuminating the surface at specific angles to reveal topography. Spectrometers need different lighting to identify surface composition. The radar works best when looking straight down through the ice. Mission planners spent years designing a sequence of flybys that balances these competing needs. Some passes prioritize imaging. Others focus on spectroscopy or radar. A few are optimized for sampling material above the surface, flying through regions where plumes might be active. The word "might" appears frequently in mission documentation. Plumes remain one of Europa's biggest mysteries. Hubble spotted what appeared to be water vapor erupting from the surface in 2012. Additional observations in 2014 and 2016 found similar features. These weren't continuous geysers like those on Saturn's moon Enceladus. They appeared intermittently, visible during some observations but absent during others. More recent observations haven't confirmed the plume detections. James Webb Space Telescope looked for plumes in 2023 and found nothing. That doesn't mean the earlier detections were wrong. It means plumes, if they exist, are sporadic and localized. This uncertainty shaped Clipper's design. The spacecraft carries instruments specifically built to detect and analyze plume material. But it doesn't depend on plumes existing. If Europa is actively venting ocean water into space, Clipper will sample it. If plumes are rare or absent, the mission can still accomplish its goals through remote sensing. That flexibility is critical because nobody knows what Clipper will actually encounter. Models predict certain features. Observations suggest others. But Europa has surprised scientists before. Every time new data arrives, it reveals something unexpected. Take chaos terrain. These are regions where the surface appears to have broken apart and were frozen in a jumbled mess. The first chaos terrain identified decades ago looked like enormous ice floes had drifted apart, rotated, and then frozen back together. Scientists proposed that liquid water or warm ice had risen from below, disrupting the solid surface. Higher resolution images complicated that picture. Some chaos regions show features that don't match simple flooding models. Others have characteristics suggesting multiple episodes of disruption. The process creating chaos terrain isn't straightforward melting and refreezing. Something more complex is happening. Carbon dioxide detections added another layer. Terra Regio, one of the largest chaos regions, shows concentrated carbon dioxide deposits. The carbon appears recently placed, geologically speaking. It hasn't been sitting on the surface for millions of years getting degraded by radiation. Something delivered it relatively recently. If that carbon came from the ocean, it means chaos terrain represents active exchange zones. These aren't ancient scars from billions of years ago. They're places where the ocean still communicates with the surface. That makes them prime targets for Clipper. But here's the challenge. Terra Regio covers an area larger than California. Concentrated carbon dioxide means higher levels than surrounding terrain, not a single rich deposit. The spacecraft will fly over this region multiple times, but each pass covers only a narrow swath. Finding the exact spots with the strongest signals requires careful targeting. Clipper's cameras can image at resolutions down to 50 centimeters per pixel during the closest approaches. That's detailed enough to see individual ice blocks and small-scale surface textures. But at that resolution, each image covers only a tiny fraction of Europa's surface. Taking pictures of everything at maximum resolution would require thousands of years. The mission strategy involves multiple resolution tiers. Wide area imaging identifies interesting regions. Moderate resolution imaging characterizes those regions in more detail. High-resolution imaging targets the most promising specific features. This hierarchical approach maximizes the science return from limited flyby time. Similar logic applies to spectroscopy. Clipper carries two spectrometers, one working in visible and near-infrared wavelengths, another in thermal infrared. These instruments can identify surface composition, but they need time to gather enough light for clear signatures. The spacecraft can't point both spectrometers at every interesting feature during every flyby. Prioritization becomes necessary. Mission planners have already identified dozens of high-priority targets based on existing data. As Clipper begins returning its own observations, that target list will evolve. Early flybys will reveal new features that demand closer inspection during later passes. This iterative process mirrors how Galileo explored the Jupiter system in the 1990s. That mission's early observations raised questions that later observations addressed. Unexpected findings forced mission planners to revise strategies mid-mission. Clipper will likely follow a similar pattern. One advantage Clipper has is processing power. Galileo's computers had less capability than a modern smartphone. Data had to be compressed heavily before transmission to Earth, losing detail. Clipper's systems can do more onboard processing, making smarter decisions about what data to prioritize for transmission. That matters because communication bandwidth is limited. Europa sits over 600 million kilometers from Earth at Jupiter's closest approach. Radio signals take 33 to 52 minutes to travel one way, depending on planetary positions. The spacecraft can transmit data at rates up to 14 kilobits per second under optimal conditions, far slower than your internet connection. A single high-resolution image from Clipper's cameras might contain hundreds of megabits of data. Transmitting one image could take hours. The spacecraft will generate far more data during each flyby than it can possibly send home in the weeks between encounters. Onboard systems must decide what to transmit first. Engineers program priorities into Clipper's software. Certain measurements take precedence. Data from instruments that can't repeat an observation get transmitted before data from instruments that will have another chance. But the system also allows ground controllers to request specific data sets when something particularly interesting appears. This semi-autonomous approach represents decades of lessons learned from planetary missions. Early spacecraft were essentially remote-controlled robots. Every command came from Earth. Later missions gained more autonomy, able to execute pre-planned sequences without constant ground contact. Clipper sits somewhere between, capable of independent operation but still taking direction from mission control. That balance will be tested during the mission's most critical moments. When Clipper makes its closest approaches to Europa, sometimes skimming just 25 kilometers above the surface, communication delays mean ground controllers can't respond to unexpected situations in real time. The spacecraft must handle problems itself. Radiation poses the biggest threat during these close passes. Europa orbits within Jupiter's intense radiation belts. The spacecraft's electronics sit inside a vault with thick aluminum walls, but radiation still penetrates. Over time, cumulative exposure will degrade systems. Some components will fail eventually. The question is whether they'll last long enough to complete the mission. Engineers designed Clipper's radiation vault using techniques borrowed from nuclear reactor shielding. The walls use interlocking aluminum plates that scatter incoming particles, reducing their energy before they reach sensitive electronics. But aluminum alone can't stop everything. High-energy protons still penetrate. Some will strike memory chips, flipping bits from 0 to 1 or back again. Most bit flips won't matter. They'll occur in unused memory locations or get corrected by error-checking systems. Others will cause software glitches that the spacecraft can recover from by rebooting. A few might prove catastrophic. Mission planners accept this risk because there's no alternative. Clipper must operate in Jupiter's radiation environment to study Europa. The spacecraft carries redundant systems for critical functions. If one computer fails, another takes over. If a sensor stops working, others can partially compensate. This redundancy adds weight and complexity, but it's necessary insurance. The most vulnerable moment comes during each close flyby. Radiation intensity increases dramatically as Clipper drops toward Europa's surface. The spacecraft spends only minutes in the most intense zones, but those minutes accumulate. After 49 flybys, cumulative radiation exposure will reach levels that would kill a human in hours. Some spacecraft systems will certainly fail before the mission ends. The question is which ones and when. What happens if a critical system fails during flyby number 20? Mission planners have contingency protocols. If the main computer crashes, the backup takes control and executes pre-programmed safe mode procedures. The spacecraft points its antenna toward Earth and waits for instructions. Ground controllers assess the situation and upload new commands. This recovery process takes days. The spacecraft misses its next flyby opportunity, but the mission continues. Total mission failure becomes likely only if multiple redundant systems fail simultaneously. Probability calculations suggest this scenario is unlikely but not impossible. Radiation damage is partly random. A particularly energetic particle might strike a critical component in just the wrong way, causing cascading failures. Or gradual degradation might weaken multiple systems until a minor problem triggers total collapse. NASA accepted a calculated risk by approving this mission. Previous Jupiter orbiters, like Juno, stay farther from the planet and experience less radiation. Clipper ventures closer because Europa's science value justifies the danger. But there's no guarantee the spacecraft will complete all 49 planned flybys. Mission success is measured in data returned, not flybys completed. Assuming Clipper survives long enough to complete its primary mission, what comes next? The spacecraft carries enough fuel for potential mission extensions. If key systems remain functional after the planned flybys, NASA might approve additional observations. But Clipper can't stay at Jupiter indefinitely. Eventually, radiation damage will accumulate beyond recovery. When that happens, the spacecraft has one final task. Planetary protection protocols require that Clipper not contaminate Europa with Earth microbes. The spacecraft was assembled in clean rooms, but complete sterilization is impossible. Some hardy bacteria almost certainly survived the construction process, hiding in cracks and crevices. If Clipper crashed into Europa, those microbes might contaminate the subsurface ocean, compromising future searches for indigenous life. To prevent this, mission planners will deliberately crash Clipper into Jupiter or one of the other Galilean moons when the mission ends. The intense heat of atmospheric entry will vaporize any remaining biological contamination. This controlled destruction ensures Europa remains pristine for future missions. It also means Clipper is a one-way mission. The spacecraft will never return to Earth. Understanding what Clipper might find requires understanding what scientists already know about Europa's ocean. Galileo provided the first strong evidence for liquid water beneath the ice. Magnetic field measurements showed that something electrically conductive exists below the surface. In Europa's case, that something is almost certainly a global ocean of salty water. How salty? Estimates suggest Europa's ocean contains dissolved salts at concentrations similar to Earth's oceans, roughly 35 grams per liter. Magnesium sulfate appears particularly abundant based on spectroscopic observations of surface ice. That composition matters because it affects the ocean's chemistry and potential habitability. Recent analysis of old Galileo data revealed ammonia-bearing compounds on Europa's surface, concentrated near fractures where subsurface material might have emerged. Ammonia is chemically interesting for several reasons. It contains nitrogen, an essential element for life as we know it. Ammonia also lowers water's freezing point, potentially allowing liquid to exist at temperatures where pure water would freeze. Where did Europa's ammonia come from? Two possibilities exist. It might have been present in the original material that formed Europa billions of years ago, trapped in ice and rock. Or it might be produced by chemical reactions in the subsurface ocean today. Distinguishing between these scenarios requires understanding Europa's internal chemistry. The ocean's temperature provides another clue about habitability. Tidal heating from Jupiter should keep the ocean slightly above freezing, perhaps near 0 degrees Celsius. But the ocean isn't uniformly cold. Heat flows from Europa's rocky interior toward the ice shell. Temperature gradients create circulation patterns, potentially mixing nutrients throughout the water column. Does Europa's seafloor host hydrothermal vents like those found in Earth's oceans? This question sparked intense debate in early 2026 when researchers published calculations suggesting Europa's tidal heating might be insufficient to drive seafloor volcanism. Their models indicated that Europa's rocky core cooled long ago, leaving the seafloor geologically quiet. On Earth, hydrothermal vents support rich ecosystems independent of sunlight. Microbes harvest chemical energy from compounds dissolved in hot vent fluids. These ecosystems demonstrate that life doesn't require photosynthesis. Chemical energy alone can sustain biological communities. If Europa lacks hydrothermal activity, one potential energy source for life disappears. But the debate isn't settled. Other researchers proposed alternative mechanisms that might support habitability without requiring active volcanism. Radiation from Jupiter bombards Europa's surface, breaking chemical bonds in ice and creating reactive compounds. These radiation-produced chemicals might work their way down into the ocean through a process called crustal delamination. Here's how that might work. Dense, chemically altered ice on Europa's surface becomes heavier than the ice below it. Gravity pulls the dense material downward while lighter ice rises, similar to how Earth's tectonic plates move. This overturning process could transport surface chemicals into the ocean over millions of years, providing nutrients that life might use. Another possibility involves serpentinization, a chemical reaction between water and certain types of rock. When water percolates through olivine-rich rock, it triggers reactions that produce hydrogen gas and other compounds useful to microbes. This process occurs on Earth's seafloor even without volcanic activity. If Europa's rocky interior contains the right minerals, serpentinization might generate chemical energy regardless of whether the seafloor is geologically active. These competing models highlight how much remains unknown about Europa's interior. Clipper's measurements will constrain the possibilities. Magnetic field observations can reveal how thick the ocean is and how conductive it is, providing clues about salt concentration and temperature. Gravity measurements during flybys will reveal density variations in Europa's interior, indicating how the Moon's mass is distributed between ice, water, and rock. The ice shell's thickness matters tremendously for future exploration. If the ice is only a few kilometers thick, a future lander mission might drill through it to reach the ocean directly. If the ice extends 15 or 20 kilometers deep, drilling becomes far more challenging. Clipper's ice-penetrating radar will measure thickness by timing how long radio pulses take to bounce off the ice-ocean boundary. Surface features provide additional clues about ice thickness. Chaos terrain, regions where the surface appears jumbled and disrupted, might form when warm ice rises from below, partially melting the overlying crust. The size and distribution of chaos terrain features can constrain thermal models of the ice shell. One particularly intriguing feature is Terra Regio, a region where recent observations detected carbon dioxide concentrated on the surface. Spectroscopic analysis suggests this carbon dioxide came from the subsurface ocean, not from asteroid impacts. That finding implies relatively recent exchange between the ocean and surface, possibly within the last few million years. If material from the ocean does reach the surface, it might carry chemical signatures of whatever exists in the water below. Organic molecules, if present, would be broken down by radiation quickly. But inorganic compounds would persist longer. Clipper's spectrometers will search for these chemical fingerprints, mapping their distribution across Europa's surface. The mission's most ambitious goal involves detecting life directly, though few scientists expect this outcome. One of Clipper's instruments, SUDA, will analyze tiny ice grains and dust particles as the spacecraft flies through the tenuous cloud of material surrounding Europa. Laboratory tests showed that SUDA can detect bacterial cell material in ice grains even when only 1% of the grain consists of biological matter. If Europa has plumes that occasionally erupt from the surface, SUDA might sample them. Previous observations from Hubble suggested plumes might exist, rising as high as 200 kilometers above the surface. But more recent observations with the James Webb Space Telescope found no evidence of active plumes during the periods observed. This doesn't mean plumes don't exist. It means if they do exist, they're sporadic, weak, or happening in places we haven't looked at the right times. Europa might be venting material only occasionally, perhaps when tidal stresses reach certain thresholds during specific points in its orbit. The Moon experiences maximum tidal flexing when it's farthest from Jupiter, and that's when plumes would most likely occur. Think about trying to photograph lightning. You might point your camera at the sky for hours and see nothing, but that doesn't prove lightning never happens. You need to be looking at the right place at the right time. Europa might work the same way. The surface could be quiet for months or years, then suddenly release a burst of water vapor that lasts only hours before subsiding. Clipper's trajectory was designed with this uncertainty in mind. The spacecraft won't orbit Europa directly. Instead, it will orbit Jupiter and make close flybys of Europa every few weeks. Each flyby will take the spacecraft through different regions above Europa's surface at different times in the Moon's orbital cycle. This approach maximizes the chances of intercepting a plume if one happens to erupt during the mission. The spacecraft's path will carry it as low as 25 kilometers above Europa's surface during some passes. That's remarkably close for a spacecraft traveling at several kilometers per second. At that altitude, SUDA will be positioned to capture ice grains ejected from any active plumes. Even if no dramatic eruptions occur, the instrument should still detect particles knocked off the surface by micrometeorite impacts or sputtered away by Jupiter's intense radiation. Radiation poses both a challenge and an opportunity. Jupiter's magnetic field traps charged particles, creating radiation belts far more intense than Earth's Van Allen belts. Europa orbits within these belts, and the Moon's surface receives a radiation dose that would be lethal to any exposed organism within hours. This radiation constantly bombards the ice, breaking chemical bonds and creating reactive compounds. On one hand, this makes Europa's surface inhospitable. No life could survive exposed on the surface for any meaningful length of time. But on the other hand, the radiation creates oxidants, molecules with extra oxygen atoms that can participate in chemical reactions. These oxidants might accumulate in the ice and eventually make their way down to the ocean through the processes discussed earlier. If they do, they could provide an energy source for life independent of sunlight. Earth's deep ocean vents support ecosystems using chemical energy rather than photosynthesis. Microbes near these vents metabolize hydrogen sulfide and other chemicals released by geological activity. Europa's ocean might host similar communities, except the energy would come from radiation-produced oxidants rather than volcanic chemistry. Testing this hypothesis requires understanding what chemicals actually exist in Europa's ocean. Clipper's infrared spectrometers will map the composition of surface ice in detail, identifying organic molecules, salts, and other compounds. Different materials absorb infrared light at different wavelengths, creating unique spectral signatures. By analyzing these signatures, scientists can determine what's present and in what concentrations. The mission will pay particular attention to regions where subsurface material might have recently reached the surface. chaos terrain and the areas around large fractures are prime targets. If ocean water has indeed been exposed at these locations, it might still retain some of its original chemistry before radiation alters everything beyond recognition. Temperature measurements add another layer of information. Europa's surface averages around -160 degrees Celsius at the equator and drops to -220 near the poles. But thermal cameras can detect warm spots where heat from below might be reaching the surface more easily. These thermal anomalies could mark places where the ice is thinner or where liquid water has recently been present near the surface. One instrument, reason, will be especially important for understanding ice thickness. This ice-penetrating radar transmits radio pulses downward and measures how long they take to bounce back. Ice and water reflect radio waves differently, so the radar can distinguish between solid ice and liquid water below. By measuring the time delay and signal strength of return pulses, scientists can map the ice shell's thickness across different regions. If the ice varies in thickness significantly, that tells us something important about Europa's interior dynamics. Uniform thickness would suggest a relatively stable ice shell with consistent heat flow from below. Variable thickness implies more complex processes, perhaps convection cells in the ice or localized heating from tidal friction. These variations would affect how easily material can move between the ocean and surface. The radar will also search for liquid water pockets within the ice itself. Some models suggest the ice shell might not be a solid block but rather a mixture of pure ice, slushy layers, and isolated liquid reservoirs. These subsurface lakes, if they exist, could be important intermediate environments between the ocean and the surface. They might be more accessible than the deep ocean while still being protected from surface radiation. Gravity measurements during each flyby will reveal Europa's internal structure more broadly. As Clipper approaches Europa, the Moon's gravity will pull slightly on the spacecraft, changing its velocity in ways that can be measured precisely using radio signals sent back to Earth. By analyzing these velocity changes during multiple flybys, scientists can construct a gravity map of Europa. This map shows where mass is concentrated within the Moon. A thick ice shell and deep ocean would produce one gravity signature. A thin ice shell and shallow ocean would produce another. The measurements will also reveal whether Europa's rocky interior is differentiated, with heavier elements sinking toward the core, or whether it remains a more uniform mixture. Magnetic field measurements will complement the gravity data. Europa's induced magnetic field arises because Jupiter's powerful magnetic field sweeps past the Moon every 11 hours as Jupiter rotates. This changing magnetic field induces electrical currents in any conductive material inside Europa. Salt water conducts electricity far better than ice or rock, so the strength and behavior of Europa's induced magnetic field provides information about the ocean's thickness, depth, and salinity. The magnetometer aboard Clipper will measure Europa's magnetic field during each flyby, building up a detailed picture of how it varies across the surface and over time. These measurements, combined with the gravity and radar data, will constrain models of Europa's interior structure more tightly than ever before. All of these investigations point toward a single overarching question. Does Europa have the conditions necessary for life? Notice that's different from asking whether life actually exists there. Clipper wasn't designed to search for life directly, though SUDA might accidentally detect it if organisms happen to be present in surface ice grains. The mission's goal is more fundamental, determining whether Europa could support life. That requires three things. Liquid water. Check. Europa almost certainly has a global ocean. Chemical building blocks. Probably. We've detected carbon dioxide, salts, and ammonia on the surface, all of which likely came from the ocean. Energy sources. This is the uncertain part. If the seafloor is geologically active, hydrothermal chemistry could provide energy. If not, radiation-produced oxidants might fill that role, assuming they can reach the ocean in sufficient quantities. Clipper will address each of these requirements. The mission will confirm the ocean's existence beyond any doubt, measure its properties, and determine its composition. It will assess how much exchange occurs between the ocean and surface. It will search for evidence of recent geological activity. And it will evaluate whether the Moon's internal heat budget allows for seafloor processes that could generate chemical energy. The spacecraft will also document Europa's geology in unprecedented detail. High-resolution cameras will image the surface at scales of less than 1 meter per pixel in selected areas, revealing small-scale features that might indicate recent activity. Wider area images at lower resolution will provide context, showing how different terrain types relate to one another. Scientists will use these images to construct detailed maps of Europa's surface, identifying regions of interest for potential future missions. If plumes are detected, their source locations will be prime targets. If certain areas show strong evidence for thin ice or recent water exposure, those become candidates for a future lander or even a mission that could penetrate the ice. But all of that comes after Clipper arrives in April 2030. Between now and then, the spacecraft must survive a journey of nearly 3 billion kilometers through deep space. It must execute a precisely timed gravity assist at Earth in December 2026, using our planet's gravity to accelerate toward Jupiter. And it must withstand Jupiter's intense radiation environment once it arrives, a challenge that required extensive shielding and radiation-hardened electronics. The mission engineers designed Clipper's trajectory specifically to minimize radiation exposure. Instead of orbiting Europa directly, which would subject the spacecraft to constant bombardment, Clipper orbits Jupiter in a highly elliptical path. Each orbit brings it close to Europa for a brief flyby, then carries it far away from Jupiter's most intense radiation belts. This approach allows the spacecraft to accumulate the necessary science data while spending minimal time in the harshest environment. Even so, the radiation dose adds up. Jupiter's magnetic field traps charged particles, creating radiation belts far more intense than anything near Earth. By the end of its mission, Clipper will have received a total radiation dose equivalent to several million chest X-rays. That would kill a human instantly, but the spacecraft was built to withstand it. Critical electronics sit inside a thick-walled vault made of titanium and aluminum. Cables are specially shielded. Software can detect and correct errors caused by radiation hitting computer chips. Every component was tested to ensure it could survive. But there's another challenge nobody talks about much. The spacecraft has to work autonomously for long periods. Radio signals take nearly an hour to travel between Jupiter and Earth, so real-time control is impossible. If something goes wrong during a flyby, the spacecraft must recognize the problem and fix it before ground controllers even know there's an issue. That requires sophisticated onboard systems capable of monitoring spacecraft health, diagnosing problems, and executing contingency plans without human intervention. NASA tested these systems extensively before launch. Engineers simulated every failure mode they could imagine, then programmed responses into Clipper's software. The spacecraft knows how to save itself if it detects anomalies. It can switch to backup systems, adjust its orientation, or abort a flyby if necessary. This autonomy is essential because each flyby happens fast. At closest approach, Clipper races past Europa at several kilometers per second. The entire science observation period lasts only a few hours. Miss that window and you have to wait weeks for the next opportunity. The 49 flybys are carefully choreographed. Each one targets a different region of Europa's surface, gradually building up global coverage. Sun passes focus on the leading hemisphere, the side that faces forward as Europa orbits Jupiter. Others examine the trailing hemisphere. Several flybys are dedicated to high-priority targets like Terra Regio, where carbon dioxide and salts indicate recent exchange with the subsurface ocean. The lowest altitude passes, skimming just 25 kilometers above the surface, are saved for later in the mission after engineers gain confidence in the spacecraft's performance. What happens after Clipper completes its mission in 2034? The spacecraft won't have enough fuel left to return to Earth, and leaving it in orbit around Jupiter poses a contamination risk. There's a small chance, probably very small, that microbes from Earth could have hitched a ride despite NASA's strict sterilization procedures. If Clipper eventually crashes into Europa, those microbes might contaminate the subsurface ocean. That would be an ethical disaster, potentially compromising one of the solar system's best chances for finding life. So NASA plans to deliberately crash Clipper into Jupiter or one of the other Galilean moons at the end of its mission. This is called planetary protection. The Galileo spacecraft met the same fate in 2003, plunging into Jupiter's atmosphere to prevent any possibility of contaminating Europa. Clipper will likely follow suit. The exact disposal method depends on what orbit the spacecraft is in when it runs out of fuel, but the principle remains the same. We don't contaminate worlds where life might exist. Assuming Clipper succeeds, what comes next? The mission's findings will shape future exploration strategies. If the ocean appears highly promising, with strong evidence for recent geological activity and abundant chemical nutrients, NASA and other space agencies will likely prioritize a Europa lander. Such a mission would face enormous technical challenges. Landing on Europa's icy surface is difficult enough, but the real goal would be to access the subsurface ocean. That means drilling through kilometers of ice, an engineering problem we haven't solved even on Earth in comparable environments. Antarctica's Lake Vostok sits beneath nearly 4 kilometers of ice. After decades of effort, Russian scientists finally reached it in 2012, but the drilling process was slow, difficult, and raised contamination concerns. Europa's ice is colder, harder, and possibly thicker. It exists in a vacuum with no atmosphere to moderate temperature swings. And any mission there must be completely autonomous because of the communication delay. You can't have a human geologist making decisions in real time. Some mission concepts bypass the drilling problem entirely. Instead of landing, they would fly through Europa's plumes, if those plumes actually exist and can be reliably detected. A spacecraft passing through a plume could sample ocean water directly, analyzing it for signs of life without ever touching the surface. But that approach depends on plumes being active when the spacecraft arrives. Current evidence suggests they're intermittent at best, possibly erupting only when Europa is at certain points in its orbit. Timing a mission to coincide with a plume eruption is risky. Another possibility is an ice-penetrating probe. This concept envisions a nuclear-powered device that melts its way down through the ice, trailing a communication cable behind it. Once it reaches the ocean, it could deploy sensors to measure water properties, search for organic molecules, or even look for moving organisms. This sounds like science fiction, but NASA has funded preliminary studies. The technology isn't ready yet, but it might be within a few decades. All of these future missions depend on what Clipper discovers. If the spacecraft finds that Europa's ice is thicker than expected, or that the ocean has less interaction with the surface than hoped, enthusiasm for a follow-up mission might cool. If it finds strong evidence for thin ice, active plumes, and rich chemical exchange, the case for a lander becomes compelling. That's why Clipper's reconnaissance is so crucial. It sets priorities for everything that follows. There's also the broader question of what Europa tells us about life in the universe. If we find even simple microbes in Europa's ocean, that discovery fundamentally changes our understanding of biology's prevalence. Life on Earth might not be a unique miracle, but rather an inevitable consequence of liquid water and chemical energy. And if it happened twice in one solar system, it probably happened countless times across the galaxy. On the other hand, if Europa has all the right ingredients but remains lifeless, that suggests life is rarer than we thought. Either answer matters. Europa represents something profound in human exploration. For most of history, we could only wonder about other worlds. Now we build machines capable of traveling billions of kilometers to investigate them.